Hi friends, now we will have a tutorial session in which we will solve some numerical problems based on last 4 classes. The first problem, the statement says estimate the temperature rise of water in a 100 liter thermosiphon solar water heating system during a typical day of operation. Assume system has one flat plate collector having absorber plate area of 2 meter square and 5 kilowatt hour per meter square solar radiations fall on collector during a typical day. Collector efficiency is 50%. Also calculate the electricity saved due to use of solar water heater and corresponding reduction in monthly electricity bill. Assume electrical geyser has efficiency of 95% and cost of electricity is rupees 3.5 per unit. So, this is the problem statement. So, we have to calculate the electricity saved due to use of solar heater and corresponding reduction in monthly electricity bill. Now, this is a problem on solar system, that is solar thermal system is available and it is used to heat the water. Now, we will see how to solve this. So, if we get the heat balance, the energy absorbed in collector during a day, that is equal to enthalpy change of the water. The solar heat will be, the solar energy will be converted to the heat energy of the water. So, energy absorbed in the collector during a day is equal to enthalpy change of water. So, this is the energy balance equation. So, now we will see the enthalpy change of water. So, that is equal to mass of water to be heated per day into specific heat of water into temperature difference. So, what is the temperature rise? Then in our case we have 100 liter thermosiphon solar water heating system. So, 100 liter means equivalent to 100 kg, that is 1 kg per liter the density of water is, and then specific heat of water is equal to 4.2 kilojoule per kg per degree centigrade, and temperature difference or temperature rise in this case equal to del T degree C. So, that is equal to we are getting 420 into del T. So, what is the temperature rise that we have to calculate. So, energy absorbed in the collector during a day, that is equal to solar radiations incident on collector per day into collector area into efficiency. So, the collector efficiency. So, then in our case the solar radiation incident on collector per day is given. So, that is equal to 5 kilowatt hour per meter square. So, this is our solar radiation on that particular day, and then 2 meter square is our area, and then efficiency is 50%. So, 5 into 2 into 0.5, then we are getting 5 kilowatt hour. So, now 5 kilowatt hour, that is equal to 5 into kilojoule per second, then if we multiply it by 1 hour, that means 3600 second. So, we are getting 5 into 3600 kilojoule of energy which is coming through the solar system. Then we have energy taken by the water, and now we are getting the energy received. Solar energy converted into heat form in water is equal to this much. So, this 5 into 3600, that is equal to 420 into del T. Then del T is equal to 5 into 3600 divided by 420. So, that is equal to 42.9 degree centigrade. So, this is the temperature rise of the water. The next part of the problem we have to solve. So, here electrical geyser has efficiency of 95%, it is given. So, electricity saved is equal to how much? So, whatever we are getting this amount of energy which is converted by the solar system and given to the water, that amount of energy would have come from the from the electricity. So, that is equal to this 5 into 2 into 0.5, but the efficiency is 95% for the system geyser. So, geyser has some efficiency 95%. So, we have to divide it by 0.95 to get the actual energy, electrical energy required to heat the water to raise its temperature by 42.9 degree centigrade. Then this much of electricity we are able to save by the use of this solar system. Then the price of 1 unit is equal to 3.5, and this is the kilowatt hour. So, that is our unit. So, we are having 5.26 into 3.5, that is equal to rupees 18.42. So, this is our save per day. Okay. So, reduction in monthly electricity bill is equal to this 8.42 into 30, that is rupees 553. Now, we are coming to problem number 2. So, the statement says calculate the efficiency of flat plate collector having absorptivity at 0.96, temperature of fluid inside the tubes is 31 degree centigrade and ambient temperature is 23.2 degree centigrade. Then transmittivity of glass cover is 0.92, assume collector efficiency factor is 0.88 and about 936.8 kilowatt per meter square solar radiations incident on the collector with heat transfer coefficient as 43.67. So, this is the problem statement. We have to calculate the efficiency of the flat plate collector. Now, as already we have discussed in previous class on solar energy, that collector efficiency is equal to useful energy gain by solar radiation incident on the collector. So, useful energy gain is equal to QU and AC is the collected area and IT is our incident solar radiation on collector. So, this is the expression we have, and we have also discussed that QU is nothing but this one. It will depend upon the collector efficiency, it will depend upon absorptivity of the collector, and then transmittivity of glass cover. It will also depend upon the loss of heat transfer loss. So, overall loss coefficient and temperature difference between the water and the ambient temperature. So, that is temperature of fluid in the tubes and ambient temperature. So, that we have discussed, and Q can be presented that way, and by simplification the efficiency is equal to Q by AC by IT, just we have in the previous slide. So, that is equal to FR tau into alpha minus FR UL TFO minus TA by IT. So, in this case, in our case FR is given as 0.88, the efficiency factor, the collector efficiency factor 0.88, then tau is equal to given as 0.92 transmittivity, and then absorptivity coefficient is equal to 0.96. So, these are given. So, here transmittivity this one and absorptivity is 0.96. So, these are given, and UL is also given. This is UL is equal to 43.67, it is given. So, that is the loss in the heat transfer or heat transfer coefficient, and then temperature of fluid inside tube is given 31 degree centigrade. So, outside is also given TO. So, now TFO we have got, TA we have got, that is TA is equal to 23.2, and IT we have got IT also, that is equal to 936.8, IT is equal to given here 936.8 kilowatt per meter square. So, if we put these values in this expression, then eta equal to 0.88 into 0.92 into 0.96 minus FR 0.88 into LUL, that 43.67 into 31 minus 23.2 divided by this IT, that is equal to 936.8. So, we are getting this equal to 0.4572, or in percentage it is 45.72%. Now, Now, coming to the next problem, problem number 3, and it states that a home requires 60 kilowatt hour of heat on a winter day to maintain a constant indoor temperature of 25 degrees centigrade. Then how much collector surface area does it need for an all solar heating system that has a 30% efficiency? So, this is our first part of the problem, and the second part, how large does the storage tank have to be to provide this much energy? So, we can assume that the average solar radiation in winter is about 6.5 kilowatt hour per meter square day, and water of hot fluid in secondary loop is 60 degree centigrade. The heat capacity of water is 1 kilocalorie per kg per degree centigrade, and heat transfer loss in water can be ignored. So, these are our conditions it is given, and we have to calculate the surface area of the collector, and we also have to calculate the storage volume, the water volume actually which has to be stored for the transfer of heat absorbed by the system and transferred to the water. Since the average solar radiations in water is about 6.5 kilowatt hour per meter square day, and the efficiency of the system is 30%, efficiency is given as 30%, and this is our total solar radiation. So, daily the quantum of thermal energy obtained using these collectors, that will be 6.5 kilowatt hour into 30%, 0.3, that is equal to 1.95 kilowatt hour per meter square day. So, this is our effective energy which we are able to get into heat form in the water, which can be transferred into the water. Therefore, the required collector surface area, what will be the collector surface area? We need 60 kilowatt hour, we need 60 kilowatt hour. So, then for 60 kilowatt hour, we for 1 meter square provides 1.95 kilowatt on that day. So, 60 divided by 1.95 equal to 30.769 meter square is the collector area which will be required to get the sufficient amount of energy to maintain the room temperature at 25 degree centigrade. And in the second problem, second part, as there is no heat transfer loss. So, what we can assume that the heat generated by the solar system is equal to heat taken up by the water. So, heat generated by the solar system is equal to how much? We have 60, this is our 60 kilowatt hour. So, 60 kilowatt hour that heat is required. So, that heat is required. So, 60 into, so it was in kilowatt hour, we have to convert it into kilocalorie. So, this is the relationship, 1 kilowatt hour is equal to 860.421 kilocalorie. So, this if we multiply 16 to 860.421, so that will be in kilocalorie unit. So, this amount of energy is coming from the solar system. Then heat taken up by the water is equal to mass of water into heat capacity of the water and temperature difference. So, mass of water we have to calculate here, and then heat capacity 1 kilocalorie per kg per degree centigrade is given, and temperature difference as it is given, say the hot fluid in secondary loop is at 60 degree centigrade and ambient temperature is 25 degree centigrade. So, the difference is 60 minus 25. So, we are getting that mass of water into 35 kilocalorie. So, this is the kilocalorie when mass will be in kg unit. So, this energy and this energy will be same. So, 16 to 860.421 kilocalorie is equal to mass of water in kg into 35 kilocalorie. So, same unit we are having. So, mass of water in kg, that is equal to 60 into 860.421 divided by 35, that is 1475 kg. Now, the density of water is 1 kg per liter. So, that will be 1475 liter also. So, 1475 liter of the storage tank it should have. Next we are coming to problem number 4. So, here the statement says calculate the power in the wind if the wind speed is 20 meter per second and blade length is 60 meter, assume the density of air as 1.23 kg per meter cube. So, it is very simple, we have to calculate the power in the wind if the wind speed is provided and the blade length is also provided. So, what is our basic expression? The wind power formula, that is P is equal to half into rho into A into V to the power cube, where rho is the density of air, A is the surface area on which the wind is blowing, that is related to the diameter of the rotor, and then V is equal to wind velocity. So, in our case, what is our wind velocity, wind speed, that is equal to 20 meter per second, it is given, and blade length L is equal to 60 meter. So, this is our rotor. So, this is a blade. So, this is our so 60 meter. So, when it will be rotating, so this area will be covered. So, this is the area A, which we are getting that A, and V is the wind speed already 10 meter per second, and then rho is the 1.23 kg per meter cube already given. So, we will put this value here. So, we have to calculate the area. So, area is equal to, so now equal to pi r square. So, pi, this is r equal to L here. So, this is our L. So, pi into L square. So, pi L square. So, pi into 60 square, that is 60 meter. So, 60 square. So, that is equal to 11,309.7 meter square. And then now we have got A value, rho value and V value. We will put this value here to get the value of P. So, P is equal to half into 1.23 kg per meter cube into 113097 meter square into 20 meter per second cube, that is equal to, it is coming 55.64 megawatt. In this unit we will get the kilowatt. So, it is converted to the kilowatt is converted to megawatt here. Problem 5, here the statement says the calculate the power that can be extracted from the wind if wind speed is 15 meter per second. Assume mechanical efficiency, electrical efficiency and transmission efficiency as 70%, 60% and 65% respectively. So, in wind turbine the wind speed is given and it is also given the different efficiency of the different processes, that is mechanical, electrical and transmission. As you know, the formula P star is equal to 0.37 into mechanical efficiency and electrical efficiency into transmission efficiency into V by 10 to the power cube. Then mechanical efficiency here is equal to 0.7, electrical efficiency here is equal to 0.6 and transmission efficiency is equal to 0.67. So, we will put this value here and our V is given 15 meter per second. So, we will put it here. So, then this expression we are getting, that is equal to 0.3409, but here the P will be in kilowatt per meter square unit as per the expression. Next we are coming to problem number 6. The statement says the calculate the rotational speed of a wind turbine in RPM having blades of 1 meter length, 1 meter blade. Assume wind speed to be 11 meter per second and tip to speed ratio be 7. So, these are the conditions it is given. We have to calculate the rotational speed of wind turbine. So, wind turbine, what is the rotational speed, and then the blade length is given, that is 1 meter, and wind speed is also given 11 meter per second, and tip to speed ratio is equal to TSR, that is equal to 7. So, now we have seen that there are some relationship between the tip speed ratio and the RPM. So, here tip speed ratio TSR is equal to 2 pi Rn by 60 V, we have already discussed in our previous class, and where this R is the radius at which SR is calculated. So, if we have a turbine blade here, rotor. So, if I want to calculate the tip ratio at the tip here or at the axis any point, I can get the SR. speed ratio I can calculate at any point. So, maximum is our length of this. So, then r is the radius at which SR is calculated, any value. So, the maximum is the full length of the blade. Then n is the RPM of the rotor, and then V is the wind speed. So, now we have the expression. Now, TSR we have to maintain as 7. So, TSR is 7, this V is equal to 11 meter per second, that is the velocity of wind, and R or length of this is equal to 1 meter, it is given. So, then by this expression we have to calculate the N. So, N is equal to, we are getting 60 V TSR divided by 2 pi into R. So, we are getting 60 into 11 into 7 divided by 2 into 3.14 into 1. So, then it is coming to 735.66 RPM. So, this is the RPM of the rotor for the wind turbine we will be having. Our last problem statement says the rated output power of a wind turbine model at wind speed of 15 meter per second is 3 megawatt. The rotor diameter is 90 meter. The rotor rotates at a constant efficiency of 0.198 hertz. Calculate the tip to speed ratio and power conversion coefficient of this model. So, assume density of air as 1.225 kg per meter cube. So, this is the condition given. We have to calculate the tip to speed ratio and power conversion efficiency of this model. So, if we think about the relationship between angular velocity and linear velocity, so that linear velocity of the tip Vt will be equal to angular velocity into radius. So, of this, so if it is a fan is moving, so then will be the radius value, and after some certain time it is making some angle. So, omega into r, that is equal to Vt, that we know it very well. So, but this omega, that is equal to the 2 pi into f. What is this omega? That is equal to 2 pi into f, that means f is the frequency. So, per second how many revolutions? One revolution 2 pi degree. So, 2 pi into number of revolution f frequency. So, 2 pi into frequency into d by 2, that is equal to 90 meter by 2. So, rotor diameter is given. So, rotor diameter is given with the blades. So, here this is 90. So, this will be half d by 2, total is d. So, d by 2 we are getting. So, then this value is coming 56 meter per second. So, 56 meter per second is the linear velocity of this, of the tip. Then the tip to speed ratio r is equal to Vt by u, that is equal to tip speed by the speed of the wind speed. So, 56 meter per second we are getting for the tip speed, and then 15 meter per second is the wind speed. So, r is equal to this by this equal to 3.7. So, that is tips to speed ratio we are getting 3.7. And the second part, the wind power at the wind speed of 15 meter per second equal to half into rho into V q, or here u q. So, what is this we are getting in this case? Half 1 by 2 into 1.225, that is given for rho, and A is equal to phi into 90 by 2 square. So, 45 square into 15 meter per second to the power cube. So, this is, so then we will be getting equal to 13 megawatt. So, the wind power has the energy potential of 13 megawatt, but the plant is giving us 3 megawatt. So, the conversion efficiency is 3 megawatt divided by 13 megawatt, that is equal to around 23%. So, now we have solved number of problems based on our previous classes, and thank you very much